I'll put this here. So yeah, Heike, you can share your video if you want, then I can introduce you. So we have Heike Rauer as our next speaker. She is the Plato Principal Investigator, the head of the Instrument Consortium, and she's at the German Aerospace Center, or DLR. So Heike, if you can hear us, you can share your presentation. We can't hear you right now. She's still on, Tracy?
Work now? Hello, do you hear me?
Yes, now we can see you. Yes.
Yeah, sorry, I just had a problem with the line. It broke down, but here I'm back. All right, so my name is Heike Rauer. I will tell you a bit about future transit missions. So wait a moment, I have to share my screen. All right, can you see my slides now?
Yes, we can. Thank you.
Okay, great. So the title of my talk is The Future of Transiting Exoplanet Searches from Space in the Next Decade. But before going into this, I want to remind all of us about what transiting planets can provide to us. Of course, not every planet and every type can provide everything, but there's such a wealth of information to be obtained by transiting planets, like their radii, their densities, if we can combine it with radial velocity masses. Even the shape of giant planets, their bladeness can be determined, love numbers, so the concentration of their mass to the interior. We can constrain interiors from all of these, their inner composition. We can obtain phase curves. We can do atmosphere spectroscopy with them. And so we can do this to characterize individual planets. But in future, we also want to get all this information for many planets and do population studies, which goes beyond mere demographics, but really studies of what kind of planets and what properties of planets do we have out there. So you've seen this kind of plot drawing the planet Mars over the semi-major axis, I think plenty of times, I guess, during this week. And I looked at Exoplanet EU, and they already claim more than 6,000 planets. But if I nail it down, which one of these planets are small in the sense of less than 10 Earth masses and smaller than 2 Earth radii? We only have a couple of hundred. And it's also remarkable how all the planets detected are somehow in this upper part of this diagram, in the upper part of the diagonal. And here in the lower part, we still have nothing. So there's a lot of work to be done, a lot of work for you to be done to fill this diagram. Another way of explaining it or showing where we are is when you plot the mean density of the planets over their mass. And this is what I've done here. You see this typical V-shaped diagram. On the right branch, we are at the high masses, larger than Jupiter masses. You see the gas giants on the, sorry, I have a problem with a cold. On the left branch, we see the super Earth and the mini Neptune planets. Venus and Earth are here, and here are Mercury and Mars. Neptune and Uranus are here in the middle. So you can see we have lots of planets already detected, but here I plotted all planets. If I plot those planets that are small and probably terrestrial planets or mini gas planets, mini Neptunes, on longer orbital periods with known masses and radii, you see larger than 80 days orbital period, we are almost empty. We are better populated on the gas giant branch with precisely known parameters, but here on the left branch, there is basically nothing except the solar system planets. So there's a lot to be done if you want to characterize planets for their properties. And that's where I see the future of transiting planets. So now, coming to the talk, what is ahead of us in terms of transiting surveys from space. I've used a figure that Karl Stapelfeld made for a review a few years ago in 2021. So today is not here anymore. Today is now here where the green line is. We are in 2025. And we have a couple of missions still running from the early 2020s. There's TESS. TESS has been extended. It's still running, and it still will probably go ahead even beyond of today. And on the European side, we have the mission called CHEOPS. CHEOPS is not a detection mission. CHEOPS is a mission that observes known planets to better characterize their transits, so to better characterize their parameters. And also CHEOPS has been extended and is still running today, and hopefully we'll get another extension. So that's what's up in space now. James Webb is up, of course, but what is ahead? As I just explained, what is missing is really a better study of exoplanet populations. Populations in detections at large orbital distances, low masses, but also populations of characterizing these planets further for their properties. And on the US side, ready to launch is the Nancy Roman telescope here, which hopefully will be launched very, very soon. On the European side, we have the Plato mission, and coming ahead. Plato is ready for launch at the end of 26 or beginning 27. And there is a Chinese mission, Earth 2.0, also ready to be launched this decade. These missions, these transiting missions, transit detection missions, will be followed by Ariel. Ariel is a mission observing known transiting planets and characterizing them for its atmospheres. And I think you have heard about Ariel already this morning. So these kind of missions, they will conclude an era. They will conclude an era of planet population studies for planet parameters and atmosphere parameters, and leading into the next era, the future, where we want to understand the atmosphere, the chemistry of planets even better, but in particular, we want to search for biosignatures in these planets. So that's ahead in the far future. But today, we have a huge job to do to finish our population demographic studies and populations of characterized planets. So let's start. I start with the mission that's next to launch. The Roman Galactic Bulge Time Domain Survey. Time Domain Survey already tells us it's not a dedicated transit telescope alone, but Nancy Roman will observe microlensing events. It's a single dish telescope, 2.4 meter diameter single dish, and here you see it in the clean room with the telescope standing on top of the satellite bus. So it's real, it's there, it's ready to go. It's scheduled for launch this year. As I said already, the telescope size is 2.4 meters. And big telescopes typically have a small field of view, and this is also here the case. Small or big, it depends what you, with 6.8 by 0.4 degrees, which is big for big dish telescope, but smaller compared to TESS and other transiting missions that we are used to. So here's the field of view of TESS. It will do 5 pointings near the galactic bulge, and then a final pointing to the galactic center. So it's really designed to detect many planets and to provide precise planet occurrence rates, including at Earth. So really going down to Earth-sized planets, and that will, as we see in the next slide, really be a breakthrough for our planet occurrence studies. So it will do these 6 observations, 72 days each. with 12 minutes cadence, so an image every 12 minutes, and a bit then a minute exposure times. And what do we expect? What do the predictions tell us about detected planets? Well, simulations going down to 21st magnitude for the target stars predict 60,000 to 200,000 transiting planets. This will be outrageous for demographics studies. However, 90 to 95% of these planets will be giant planets. The planets, because they are orbiting stars that are so faint, will only have a limited capability to do radial velocity on them. Typically, precise radial velocity needs bright targets, 11th magnitude or brighter. But it will be of really huge value for planet statistics. And if you see in this plot here, where they show the planet Mars over the semi-major axis, the Venus Earth is here. The blue-greenish dots mark the transit detections. Yellow dots mean detections coming from microlensing that Roman is doing as well. And you can see what range is covered, mainly here the gas giant range, but in the microlensing survey, they even go down to planets as small as the Earth, fainter, with a sizable number of detections. So with these two techniques, transits and microlensing overlapping, they cover a really large range of this population diagram, mass distance diagram. So I'm very much looking forward to this mission and to these planets and what it will tell us about demographics, in particular in the range down here that is not covered so far. So Roman will be the first to really touch that. The next mission to launch is Plato. Plato is also getting real. Plato is a mission that is not a single dish design. It's rather unusual for a telescope. Instead, Plato has 26 individual cameras, and they sit on on this optical bench. You see the cameras in the clean room here. And to the right, you see this optical bench, but you see it from the bottom. Yes, the bottom side of the optical bench on a crane, just being lifted on top of the satellite bus. Meanwhile, that has happened, it's completed. So also Plato is there in the moment in Munich. It will go to ESA soon in autumn, and the solar panels will be attached, and then the spacecraft is also ready to be launched in 2026. So here you see a little movie that shows how this will look like at the end with these 26 cameras on the satellite. Each of these cameras has 12 centimeter aperture. That's similar to TESS. I think if I remember well, TESS has 10, 11 centimeter aperture. So we have also a similar field of view of each camera. However, the cameras are a little bit displaced. This you will see in the next diagram. So we get a very wide field of view of the satellite altogether with 49 by 49 degrees field of view. It will perform high precision photometry as we need it for transits, mainly in the magnitude range down to 11, 13th magnitude. We have been given 4 years mission operation time by ESA. However, the satellite will carry 8.5 years of consumables. So if we get mission extensions, we can stay longer. And that's, of course, what we hope for. And the goal is to detect and characterize planets. And why do I emphasize this so much? Well, you already know what you learned from transits, the planet radius and the inclination. We will also perform an intensive astroseismology program on target host stars, but also on stars in the field to improve our knowledge of stellar parameters and get the host stars stellar parameters very precisely, and to get the stellar age. The stellar age tells us also the age of the planets because planet formation is so fast. And that is therefore a key parameter for Plato. And this will be combined with an extensive ground-based observing program to derive the planet masses And putting all this together, we have the planet mean densities and their age. Mean densities, because mass radius densities help us to constrain planet interiors, help us determine the nature of the planets, and ages, because my big dream is that we have, not from Plato alone, but combined with all future missions, we have so many well-characterized planets at different ages that we can really look at the evolution of planets by looking at populations of similar planets around similar stars at different stages of their evolution. That's my big vision, and Plato is a little step in this big vision, and putting it all together with the atmosphere missions and the future missions, I think we are getting close to this in the years to come. There's a lot of exciting stuff for you to be done. So here another, I don't want to go into all of these details about Plato, but it's my instrument, so I hope you forgive me. I'm a little bit more in detail here. As I said, we have these 12 centimeter cameras, 24 so-called normal cameras. They operate in white light. You see one of them here in a test equipment. They are mounted on this optical bench, but in 4 groups, and these 4 groups are a little bit, they diverge in their field of view a little bit. So we have one group forming such a circle of field of view, then the other group being a bit displaced, and so on. So you often see this kind of flower pattern with Plato, where in the center we have all 24 cameras watching the same part of the sky, and in the corners it's 6 cameras looking at the same part of the sky. We have a readout cadence of our CCDs every 25 seconds. And then there are 2 fast cameras. They point to the center of the field of view. They are used to ensure the very precise fine guidance of the satellite. And they are called fast because they are read out every 2.5 seconds. And one of them has a blue and one has a red coating to provide some color information, mainly for our stellar colleagues. So Plato, where we look at, this is the sky in galactic coordinates. Here is the Kepler field. And the green pointings are the pointings of Kepler. The little red dots here are the French French-European Corot mission fields. And the big blue pattern is Plato. So you can see the comparison of the Plato field to Kepler. So we have a field in the north and we have a field in the south. They are very much constrained by straylight requirements. And we decided to start with the southern field. Our baseline in the 4 years operation time we are given now by ESA is to observe 2 years in the south and then 2 years in the north. And all the numbers I'm giving refer to two target fields. If we decide to stay in the south, to go for a longer period planet, even longer period planets, then of course these numbers have to be divided by half. Okay, so we will observe 15,000 stars with brighter than 11th magnitude, and for characterizing their planets as precisely as possible. And then we have a larger sample of more than 200,000 targets, which we call the statistical sample. So here the performance of Plato will be like Kepler. They are mainly too faint to do radial velocity follow-up, so they are really for population demographic studies. And in addition, we have a smaller sample of M dwarfs down to magnitude 16. And triggered by Jesse's talk, I want to say a word on our data analysis, because we don't publish just the light curves, at least for the targets in our prime sample, these and the bright stars, these 15,000. We will provide a catalog of planet parameters derived by our pipeline. So this will be a catalog of parameters derived with a homogeneous procedure, a homogeneous pipeline, and that should fulfill the requirements for planet demographics, at least triggered by our colleagues from the Kepler team here, thanks to Jan Jenkins in particular, who made us aware of all the things we have to take into account. We are really planning demographics analysis from the beginning in the pipeline analysis. So that's again summarizing what we want to do. This plot shows stellar masses versus semi-major axis of planets. It shows the habitable zone as this green belt. All the circles are detected planets. And for our planet characterization, to constrain the interior, you need very precise masses and radius. Even if you get them extremely precise, it's not enough to be sure about your interior because it's a degenerated problem. But the minimum we can do is to minimize the errors just coming from measurement errors, right? With precise planets and masses, you see, we get them now for M-dwarf stars down here, but up here where we have the sun is here, so solar-like stars, it's only our solar system, and that will not change. And that's where our Plato mission is targeting it. All right, so what do we expect? Well, depending on observing strategy, we are now here in this strategy. We are in the range of thousands of stars, maybe 0, maybe 100 Earths. We will know. Eta Earth is unknown. We will see. But this is a study that was recently been published by Yoshi Eshen. What she did, she compared the sensitivity of Plato to TESS, using 12 TESS observing cycles and comparing to one of the 2 years of Plato. And we see here the orbital period, the planet radius, and the color marks the sensitivity. So pure yellow is clear detection. And you can see how Plato will really push the sensitivity limit for planet detection down here to where we want to go. That's Earth-sized terrestrial planets far out. All right, let me move to the next mission that's coming, the Chinese mission, Earth 2.0. And you see here on the sketch of the mission, we are again, like with Plato, on a multi-camera design, so not a single dish. And this mission is scheduled to launch in 2028. We have 6 telescopes, larger than Plato, so more approaching the size of a Cheops telescope, which is 32 centimeters. Here we have 28. These 6 telescopes give a large field of view, 550 square degree, and the pointing will be the Kepler field. So they want to point north, centering on the Kepler field, but because their field of view is much larger, they also cover a lot of new sky that has not been searched for planets yet. And they are expecting a yield of about 40,000 transiting planets. And if we look at this plot here, they make predictions depending on the class of planets. So Jovian, Neptune, super-Earth we have here. You see that's their main peak is in the Neptune, mini-Neptune and super-Earth regime, but with 10,000 of planets each. So we are really looking forward to this one. And finally, I want to show you this mission comparison to give you a little bit of flavor. What's the difference of all these missions? So the detection rate of a transit mission is really determined by the telescope aperture and the field of view. Of course, the duration and so on, but these 2 parameters help characterizing a survey. So if you have a small telescope size, it means you want to observe bright stars, which is important if you want to get planetary masses from radial velocity, because then the stars can't be too faint. Yeah, if you go much below 11th magnitude, 12th magnitude, it's really getting difficult, at least on a large scale. So these telescope missions in this class were the Kourou mission, TESS, with the individual cameras are small, Cheops, and also Plato with small camera or telescope apertures. These missions, many of them, because they are not Cheops, but the others, because they target bright stars. They also allow for astroseismology of the host stars to determine ages, which is another important parameter one can get from them. If you go for a large telescope size, like Kepler, Roman, or Earth 2.0, you of course increase the number of detected planets because you can go fainter. Yeah, we have seen with Roman it's down to magnitude 20, and that means many more target stars and of course many more detected planets, and that's very good for population studies. If you provide a large field of view, of course, a large field of view you can obtain by with a wide field of your telescope. But TESS, Plato, and Earth Point 2 went to the concept of having several small telescopes to increase the field of view. And TESS and Plato also use the approach not to stare at one field. Earth 2.0 will stare, they will not move. But as you know, TESS is scanning the sky, and Plato will have in the baseline 2 fields to observe. In this way, we can also increase the number of targets to be observed. So if you look at this plot here to the right, where we have field of view, here we have versus the magnitude range of the targets observed, the main magnitude range. We see Roman is down here, very faint targets and a small field of view. Corobus here in the middle, Kepler is up here. Earth 2.0 has a larger, has this multi-telescope approach, therefore a larger field of view, but a similar magnitude range to Kepler. TESS and Plato with small cameras, but a wide field of view, TESS by scanning, Plato with 2 fields. You see, TESS covers up to 80% of the sky with its scanning observing mode. This is enormous. Plato with 2 fields will be up to 10% of the sky, but both target bright magnitude for bright stars, bright magnitude ranges to allow for radial velocity follow-up. So they really want to allow for the characterization. So in summary, the exoplanet research in the next decades are driven by one class of missions like Roman and Earth 2.0. They focus on large population studies for understanding planet occurrences, occurrence rates, planet formation theories. And Plato populations of characterized planets with ages, interior constraints. And here the target of the scientific question addressed is more to understand planet evolution. Of course, we also want to constrain Eta Earth, but we want to mainly constrain the planet itself to understand evolution. And that, of course, is complemented by the atmosphere characterizations from James Webb, Ariel to come, and then in future, Habitable World Observatory and maybe LIFE. And putting all of this together in a decade from now, or 2 decades from now, if I look at the very far right here, it will be an enormous data set. And it will be so exciting to put all of this together once and learn about planets with so much different environments, different stages of evolution. I'm really looking forward to that. Thank you.
Yeah, thank you very much, Heike, for a very nice talk. And thanks for joining us so late in Germany. It's evening.
Sorry for coughing.
No problem. If you have any questions here, please come down. In the meantime, I have a quick question. So since there's some overlap probably between Plato and the TESS observations, so is there any plan to maybe reobserve some of the targets to get more insights on the transiting planets, or maybe find new planets? I don't know. Like, is there any synergy maybe a bit between TESS and Plato?
Yes, it's a good question. We have the same question from the Cheops team. I mean, if TESS continues its scanning mode, it will pass by the Plato field in any way. Yeah, and so we are. How shall I answer this question? I can answer it historically. Historically, we had the faint sample and we had the step and stair phase to scan the sky with Plato fields for observing 3 months or so. And this mode we really dropped because TESS is there, and TESS is doing such a great job. It will do the short period planets, right? So for us, it mimics the test targets in the Plato field will be observed with a larger aperture or with more sensitivity if they are in the center. So now instead of having one test camera observing them, we can be up to 24 Plato cameras observing them. So of course, we get a higher signal to noise for the same light curves. Yeah, and then Plato will observe because it's staring, we reach out to longer orbital periods, that's clear. But on the test targets, I think it's the photometric precision that would be a plus on top of the test observations. Yeah. But I would really like to see more discussion on this synergy. We have not done so much yet, and I think there is more to be done.
Thank you very much. Any questions in the room? If you don't have any, then we'll thank Heike again. So thank you very much.
Yeah, it's a nice workshop and enjoy.